by, everyone. 45 seconds.
Have a great show, guys. Good afternoon. Welcome to NASA headquarters in Washington, D.C. My name is Dwayne Brown with the Office of Communications. On September 8th, NASA will launch the first U.S. spacecraft that will rendezvous with, study, and return a sample of an asteroid, simply called To an Asteroid and Back. Before we hear about this unprecedented mission and the incredible science return, to set the stage, coming to the stage is a gentleman who actually this past Monday celebrated 10 years of being the chief of the Planetary Science Division, the longest serving leader at that. And in those 10 years has amassed an incredible resume with the missions. For example, and I'm sure many of you are quite familiar with them, the Curiosity landing, Pluto New Horizons, and the recent Juno spacecraft orbit of Jupiter. And today you will hear about To an Asteroid and Back. Ladies and gentlemen, please welcome to the stage the Director of Planetary Science Division here at NASA headquarters, Jim Green.
Thank you very much, Dwayne. 4.5 billion years ago, in a galaxy we call the Milky Way, a cloud of gas and dust began to collapse. And we believe that perhaps that started from a supernova that exploded nearby. That collapsing gas and dust began to form primitive bodies we call asteroids today. Many of these bodies coalesced, accreted, and created our planets and the larger bodies of our solar system that we know today. But many of these primitive bodies are still available for us to look at and interrogate. One such body is Bennu. This is a dark asteroid that we have found and that we're going to hunt down, we're going to orbit, we're going to take a good look at it, and we're going to bring back a sample. This is a fantastic mission. It will enable us to learn about our initial collapsing cloud because it's such a primitive body. Make no mistake, this is not an easy mission. So today we're going to hear about the mission. We're going to hear about the asteroid Bennu itself and how NASA's going to pull this off. And so let me turn it over to our panel. Dwayne?
Thank you, Jim. Before I introduce today's panelists and their briefings, just a reminder, this will be a conversation that will go on and on and on to launch and, of course, throughout the mission. Join the conversation. There is a lot of conversation. Twitter, Facebook, YouTube. And send your questions in. We're going to take as many questions as we can from our social media audience, and I know there's a large number of you watching today. We'll try to get to them during the show, and we will also be answering questions following the program. Send those questions in at hashtag AskNASA. And of course, all of the information you will hear and see today is available online and much, much more at www.nasa.gov/OSIRIS-Rex. Okay, let me introduce you to today's panelists. First up will be Gordon Johnston, OSIRIS-Rex Program Executive at NASA headquarters in Washington. Jeffrey Grossman, OSIRIS-Rex Program Scientist, NASA headquarters. Dante Loretta, OSIRIS-Rex Principal Investigator with the University of Arizona, Tucson. Christina Ritchie, OSIRIS-Rex, Deputy Program Scientist, NASA Headquarters. Rich Coons, OSIRIS-Rex Program Manager, Lockheed Martin Space Systems, Denver. And Mike Donnelly, OSIRIS-Rex Project Manager at NASA's Goddard Space Flight Center in Greenbelt, Maryland. Okay, let's get started. Hold on to your hats and your chairs. Over to you, Gordon.
All right, thank you, Dwayne. Could I have my first graphic, please? So we're preparing to launch the OSIRIS-Rex mission. OSIRIS-Rex is an acronym. It stands for Origins, Spectral Interpretation, Resource Identification, and Security, Regolith Explorer. And Jeff, Dante, and Christina will be explaining more about the science that OSIRIS-Rex will achieve. We have a 1/10 scale model here of the spacecraft. It is about the size of an SUV. It weighs about 2,000 pounds with the fuel tanks empty. But when we fill up the fuel tanks, that more than doubles the weight to 4,650 pounds. The sample return capsule weighs about 100 pounds. It's solar powered. It communicates back with the Earth through the Deep Space Network. The total mission cost, not including the launch vehicle, but including the 7 years of operations in space and 2 years of analysis of the sample once it returns, is about $800 million. As mentioned, Bennu is a carbon-rich near-Earth asteroid that holds the record of the formation of the solar system and some fundamental questions, can answer some fundamental questions about the origins of our solar system and our planet. This will be the first return mission, sample return mission from an asteroid, and will return the largest sample from space in the last 50 years, since the Apollo era. We've already learned a lot about OSIRIS-Rex, about operating near an asteroid from what we've been doing on OSIRIS-Rex, and we'll continue to learn more once we get to Bennu. And what we learn will help us in our future exploration of asteroids, of both human and robotic. May I have the next graphic, please? OSIRIS-Rex will launch on a Atlas V rocket from the Cape Canaveral Air Force Station on September 8th at 7:05 p.m. We have 2-hour launch windows for the next 34 days. After launch, a year after launch, we'll fly by the Earth on September 22nd, 2017. In August of 2018 is when we'll be able to just see Bennu as a single pixel, a single spot in our cameras from the OSIRIS-Rex spacecraft. Then over the next 2 years, we will approach Bennu, map it, orbit it, study it, and pick the safest and most scientifically interesting place to pick a sample from before going in and attempting to sample. We will nominally acquire the sample in July of 2020, but one of the beauties of this mission design is that we have a lot of flexibility. If we discover some surprises, if it takes us longer to do some of the rehearsals, we can delay that. But our nominal sample acquisition is July of 2020. Once we've acquired the sample, we will stow it. We don't leave the asteroid until March of 2021, and we could leave as late as April of 2022. So we have well over a year of operational margin. We arrive back at the Earth in September 24th of 2023, landing at the Utah Test and Training Range. We will then take the sample to the Johnson Space Center where it will be curated and studied by the scientists of the OSIRIS-Rex team. 4% of the sample will be curated by Canada because they're a major partner in the mission, having provided the OLA instrument. 0.5% of the sample will be curated by the Japanese space agency JAXA as part of our cooperation with JAXA on the OSIRIS-Rex and Hayabusa 2 missions. But 3/4 of the sample will be set aside for future researchers for the science questions we haven't figured out to even ask yet, and the science laboratory instruments that we haven't even developed yet. And that's really the rich legacy of a sample return mission. Could I have the next graphic, please? So OSIRIS-Rex is a space mission, but it was built here on Earth. At its peak, we had the equivalent of about 450 full-time people working on the mission. And of course, many of those people were experts that were working part-time, so the number of people is actually much greater than that. The mission has components from international suppliers as well as many, many suppliers across the United States, most of them from the United States. This logo lists the major partners. We have representatives from those major partners here. Dante Loretta is from the University of Arizona, and then we have Rich from Lockheed Martin and Mike from the Goddard Space Flight Center. So with that, I'd like to turn it over to Jeff to talk about the science.
Thanks, Gordon. So NASA has been conducting science missions to explore the solar system for over 50 years, and science is what OSIRIS-Rex is all about. I'm going to try to set the mission in a little context for you in terms of our programs and what it's going to do and how we explore the solar system. If I could have the first graphic. The New Frontiers program is the program that hosts OSIRIS-Rex, and OSIRIS-Rex is the third mission in this program. This is a program that solicits medium-cost missions to explore the solar system from principal investigators who are in the community. Dante is one of them. The priorities for the New Frontiers program are set by the National Academy of Sciences about every 10 years. They update it. OSIRIS-Rex is the third New Frontiers mission. The first was New Horizons, which had a magnificent flyby of Pluto in 2015 and is now on its way to a 2019 encounter with an object in the Kuiper Belt. The second is Juno, which just entered orbit this summer around Jupiter and is beginning its science campaign there. And OSIRIS-Rex is the third, the first of the New Frontiers missions that's going to go to an asteroid. One of the amazing things about OSIRIS-Rex is it actually addresses all of the science goals that planetary science has at NASA. OSIRIS-Rex is going to help us understand how the solar system works and the nature of the bodies in the solar system. It's going to help us understand how the solar system formed. It's going to inform our understanding for the potential for life in the solar system on Earth and elsewhere. But it also advances our more practical goals of understanding the resources of the near-Earth solar system as well as the hazards and characterizing those and better understanding the processes that are involved with those. So if I can have the next graphic, please. The timeline that we do for all planetary exploration follows a fairly well-defined sequence where we start out with observations and we move on to go past the object and look at it as we go by, we orbit, eventually we land, and the big prize is we return a sample from there. This is the planetary science exploration timeline or order that we tend to do missions in. We've only been looking at asteroids for about 25 years. The first flyby was made by the Galileo mission in 1991 when it flew by the main belt asteroid Gaspra. NEAR was the first mission to orbit an asteroid, and it was also the first mission to a near-Earth asteroid. And it successfully landed at the end of its mission on the asteroid Eros. And the Japanese mission Hayabusa managed to get to a fairly common type of asteroid and return a tiny little sample from it and demonstrated that this can be done. And so we are building on this in OSIRIS-Rex and actually repeating this whole sequence. The next, please. If we could start this video. So OSIRIS-Rex is going to do this whole sequence on its own. We've already done astronomy needed to understand what Bennu looks like, and this is the shape of the asteroid. We are going to fly up to Bennu and study it from the proximity of Bennu, and then we're going to enter orbit around Bennu and study it even closer. But of course, the big prize is going to be achieved when we get a sample of Bennu. Shown here is a depiction of how that works. We're going to go down to the surface. We don't technically land on Bennu, but we make contact with it for about 5 seconds. Get a sample and put it back in the spacecraft. We're trying to get at least 60 grams, which is about 2 ounces of sample from Bennu, but we could get much more. And we could try up to 3 times before ultimately delivering it back to Earth, where we'll receive it on September 24th, 2023. So These are a return sample is really the big prize of our planetary exploration programs right now. And if I could have the next video. It's only been done a few times in history. Sample return, the first sample return was done by the 6 Apollo missions, which returned about 800 pounds of moon rocks over the course of their, in the early 1970s, late 60s. And we learned a lot about the moon and the early solar system from those missions. Then here shown is the Genesis mission, where we got atoms of solar wind collected to learn about the composition of the sun. And later, returning in 2006, we collected dust from a comet. This is the Stardust mission, where we learned about the composition of the tail of this comet, and grains from it told us a lot about the origin of the solar system in that mission. And the way we do this, of course, is we bring the sample back and we can subject it to a battery of examinations and tests that we can't do anywhere else but on Earth. And it enables not only a better understanding of these objects, but it also spurs technological innovation to get the most out of these samples. So the next 3 speakers, Dante and company, will tell us how we're going to do this exactly, what the exact science is we're hoping to learn, what the instruments are like, and why we're going to this place in the first place. So Dante?
Thank you, Jeff. If I could have the first graphic element up. So the mission objectives are captured in the awesome acronym that is OSIRIS-Rex. And it captures first the origins, and this is really the driver of our science. We seek samples that date back to the very dawn of our solar system, and we want to get those back into our laboratories to understand the processes that may have led to the origin of life and to the habitability of our planet. The spectral interpretation connects the data that we're going to collect from our spacecraft to our telescopic information of Bennu, and then by understanding and ground truthing that information, we'll be able to extend that to other asteroids throughout the solar system. The resource identification captures the drive to bring samples back from for economic reasons and for future exploration. The security focuses on the potential hazards that asteroid represents, and the regolith explorer is the material. The regolith is the dust and the gravel that exists on the surface of these airless bodies. I'm going to go through each one of these in detail to explain a little more about our science. Next, please. So the solar system began as a giant rotating cloud of gas and dust around the growing protostar that would be our sun. Inside this disk, there were compounds that were forming, minerals that were created, and they coalesced together to form asteroids, ultimately growing into planets. Certain regions of the solar system contained large concentrations of carbon and water in the form of ice and clay minerals, and we think those are critical to understanding the habitability of our planet, because early in the history of the Earth, we went through a period called the Late Heavy Bombardment, where asteroids crashed down onto the surface of our planet, sterilized it, and made it very inhospitable to life. This mission follows on the very successful Stardust mission. And in fact, we're using the same sample return technology for OSIRIS-Rex. Stardust told us a lot about comets, which formed way in the outer part of the solar system. OSIRIS-Rex is bringing back samples closer to home, and probably the likely candidates that deliver these key prebiotic compounds to our Earth and help us understand why we are here, how we are here, and how likely it is that this kind of process, origin and evolution of life, may have occurred elsewhere in the solar system and even throughout the galaxy. So it's critical. We're going after compounds that are literally at the part per billion level in these materials. We have to get these samples into our laboratories so that we can bring cutting-edge analytical techniques, the kinds of things that you just can't fly on a spacecraft because they weigh too much, or they require too much power, or they require a very careful lab technician to make the analyses possible. So sample return is the gift that keeps on giving. We're going to analyze it for our science, and we're going to have future generations looking at these materials for decades. Next, please. The spectral interpretation investigation relies on the fact that we've had a phenomenal astronomical campaign to characterize our target asteroid. We used the best telescopes on Earth and in space to learn everything possible about asteroid Bennu from these techniques. Obviously, the information is limited, and we're applying those to the over 700,000 asteroids across our solar system by bringing our spectrometers like the OSIRIS instrument that was built at the Goddard Space Flight Center and the OTIS thermal emission spectrometer from Arizona State University. We're going to get data up close and personal with Bennu. We're really going to be able to compare it to what we thought we learned from our telescopic observations. And most importantly, we're going to be identifying key organic molecules on the surface of the asteroid to guide our sample site selection. Next, please. The resource identification captures the interest and the investment that corporations and nations across the world are making in the potential for exploiting and developing asteroid. And we're going to contribute to that. In fact, we're a trailblazer for that kind of activity because our science requires it. We're going to get to asteroid Bennu, and we're going to map this brand new world that we've never seen before. We've got an extensive suite of cameras. We've got our laser altimeter from the Canadian Space Agency, the spectrometers, and the spacecraft itself. We're really going to understand the distribution of materials across the surface of that asteroid, which is going to be critical for characterizing regions of interest on the surface and ultimately making that key decision, which is where on this mountain-sized asteroid in space are we going to go down and get those precious 60 grams or more of material for our science. Next, please. The security aspect addresses the fact that we're going to a near-Earth asteroid. We're very interested in these objects for the science, but we're also keeping an eye on them for potential impact hazards. And in fact, NASA has been very responsive to congressional directives in this area. We're going to contribute to this science by measuring a phenomenon called the Yarkovsky effect, which is a fascinating interplay between sunlight and these small asteroids. The asteroids get their energy from the sun. A lot of that energy, especially on a dark asteroid like Bennu, is absorbed, causing the asteroid surface to heat up. It has to release that energy back out into space, and when that happens, it acts like a thruster and changes the trajectory of the asteroid. So if you want to be able to predict where an object like Bennu is going to be in the future, you have to account for this phenomena, and we're going to provide the best ever scientific investigation of this fascinating concept. Next. And for the Regolith Explorer. So Regolith, we've done a great job convincing ourselves that Bennu contains a lot of loose material on the surface through our astronomical campaign and our geophysical modeling. And we really want to understand the nature of the material on the surface of the asteroid. In and of itself, it's a fascinating science question, but what the real value of sample return is the geologic context, so you know exactly where those samples came from on the surface of the asteroid. This makes it incredibly important for us to do detailed sub-centimeter resolution characterization of the surface of the asteroid. It's going to be an unprecedented data set, providing all kinds of great information about Bennu, as well as giving us the critical context for the return sample. So all of these science objectives are met by the OSIRIS-Rex mission to asteroid Bennu. So Christina is going to tell you about why we chose the target and everything we know about it.
Thanks, Dante. So our main goal is to collect a sample of an asteroid and return it to Earth. But why was Bennu chosen as the target destination asteroid for OSIRIS-Rex? Well, the science team took into account 3 criteria when making that selection: the accessibility of the asteroid, the size of the asteroid, and the composition. So let's get into each one of those in detail, and we're going to start off with accessibility. We need an asteroid that we can easily travel to, retrieve a sample from, and return to Earth all within a few years' time. Go ahead and start my first graphic. The closest asteroids are called near-Earth objects, and they travel within 1.3 astronomical units of the Sun. Now, for everybody out there who doesn't think in terms of astronomical units, 1 astronomical unit, or 1 AU, is equal to approximately the distance between the Sun and the Earth, about 93 million miles. For a mission like OSIRIS-Rex, the most accessible asteroids are somewhere between 0.8, 0.8, and 1.6 astronomical units. But those asteroids actually also have to have a similar orbit to Earth, so they have to be circular and low in inclination. Bennu orbits between 0.9 and 1.6 AU from the Sun. It orbits the Sun every 1.2 years, and its inclination is only 6 degrees different than that of Earth's. It passes by Earth every 6 years, so it's easily accessible for this mission. Next up in terms of criteria was size. We need an asteroid the right size to perform 2 critical portions of the mission: operations close to the asteroid and the actual sample collection from the surface of the asteroid. Second graphic, please. Now, as I talk about size, I'm going to have to bring up the Olympics and my favorite event going on at the Olympics right now, track and field. So 400 meters is equal to 1 lap around the track. It's just under a quarter of a mile at 1,312 feet. When we're talking about asteroids, when I define the term smaller asteroid here, I'm thinking of things with a diameter that's smaller than 200 meters, so half a lap around that track. When an asteroid is smaller than those 200 meters in terms of diameter, it actually spins rather quickly. And it can rotate rapidly enough to where even some material could potentially be ejected off the surface. More importantly, it's extremely difficult for a spacecraft to match that rotation speed when it's going that quick. And it's not going to be able to potentially sample the surface. So we need to be able to be close to the asteroid for mapping, site selection, and then retrieving our sample. We want this to be a safe, smooth, slow high five of that surface. Bennu is roughly spherical. It has an equatorial bulge that's right around 492 meters in diameter, and it has a rotation period of 4.3 hours. So it's within our size criteria. Our third criteria was composition. Asteroids are actually categorized by their spectral properties. And go ahead and start my third graphic. In the visible and infrared light, minerals have unique signatures or colors, much like fingerprints. Scientists use these fingerprints to identify molecules like organics. For primitive, carbon-rich asteroids like Bennu, materials are preserved from over 4.5 billion years ago. We're talking about the start of the formation of our solar system. And these primitive materials could contain organic molecules that may be the precursors to life here on Earth or elsewhere within our solar system. Thanks to telescopic observations in the visible and the infrared, as well as in radar, Bennu currently is the best understood asteroid not yet visited by a spacecraft. And with the sample return of a known geologic context, as Dante had mentioned, we will enable precise analyses that simply cannot be duplicated by mere spacecraft observations or even by lab analyses of meteorites. So the size, orbit, and the primitive carbon-rich composition of Bennu make it a fascinating and accessible asteroid, and that is why it was ultimately chosen as the target destination asteroid for the OSIRIS-Rex mission. And with our impressive instrumentation on board our spacecraft, which Rich will talk about our spacecraft next, and with a scientifically exciting asteroid like Bennu, as well as with this phenomenal team that we have, we at NASA will be able to find out more about the nature of asteroids, thereby teaching us about the fundamentals to the formations of planetary bodies, our own solar system, and even the ingredients to the origin of life. So, Rich, tell us about this amazing spacecraft.
Thank you, Christina. So the OSIRIS-Rex spacecraft is actually the result of combining a couple of very successful heritage events. The SRC, or the sample return capsule, is coming from the very successful Stardust mission. It's almost an exact copy of what was returned to Earth on Stardust. The spacecraft itself that it was combined with is an evolution that started on MRO, or the Mars Reconnaissance Orbiter. It came through the Juno spacecraft and the Maven spacecraft, and we've adapted it to hold the sample return capsule, but it's really come from combining those two successful heritage missions and sets of missions that the spacecraft we have now exists. If we could start the first video. We started formal assembly and test operations in March of 2015. We did that in a clean room because it's so important for us to maintain the pristine nature of the samples. So we had extra controls that were required for us on this mission that we haven't had in the past. We then tested the spacecraft through a series of environments that mimic what it sees from the time that the rocket launches all the way until the sample lands safely in the desert in 2023. We tested it over temperature, we tested it over pressure, vacuum, no vacuum. We tested it in vibration environments, and we tested it through the acoustic environment that it sees during the launch environment. It really took a whole team of people in order to make sure that the efforts were successful. And as a result of those efforts, we were able to transport the spacecraft on May 20th of this year from the Littleton campus to Buckley Air Force Base, where it was loaded onto a C-17 and flown to Kennedy Space Center for future processing. One of the primary payloads that we have on the satellite is the TAG-SAM. It's the touch and go sample acquisition mechanism. Now, this actually started as a contest where we wanted to know what is the best way to actually bring back a sample from a body outside of Earth's orbit. And it turns out that somebody used a solo cup and an air compressor in their driveway, and that's what actually started the TAG-SAM technology. It's a reverse vacuum. If we can play the next clip. Over the past 10 years, it's come a long ways from a solo cup in the driveway to what you see now. The TAG-SAM arm itself is constructed of several elements, starting with the sample head itself. The sample head is about the size of a GTO air filter, so it's about a 12-inch diameter circle. It's connected to an arm that's about 10 feet long, and it has a pogo on it. And the purpose of the pogo is to keep us in contact with the asteroid for the 3 to 5 seconds it takes to give the asteroid the gentle high five. We then release the gas, which is how we actually collect the material from the asteroid and bring it back up to measure it. We've tested the technology over a wide range of different materials. We've tested it with lightweight materials, we've tested it with dense materials, we've tested it with different sizes of materials in order to understand how wide of a range of material we'll be able to collect. Throughout that testing, we've collected significantly more than we intend to collect, with an average collection over 300 grams as opposed to our target of 60 grams. So how do we use that mechanism? So if we can play the next video. The first part of using it is getting it deployed. So when we do deploy it, it actually looks like our model over here, where it's actually located above the sample return capsule. We get it in position so that we can go down and collect the sample. We then, through a series of maneuvers, get on a trajectory that puts us in contact with the asteroid. When we detect contact, we release our gas, which agitates the material and collects it inside of the sample head. Once we've released the gas and collect our sample, we go back away to a safe distance from the asteroid and we do a spin maneuver where we actually spin the satellite to try and understand how much material we have. Once we've confirmed we have enough material, we're able to stow it in the sample return capsule and place ourselves on a trajectory back to Earth. About 7 days beforehand, we get an orientation to release the sample return capsule. And that sample return capsule, when it comes in, is moving at 27,700 miles per hour, so extremely fast. On its way down, it releases 2 parachutes and ends up gently landing in the Utah test range. From there, we very carefully move it to the Johnson Space Flight Center, making sure that we maintain the pristine nature of the sample, and then we store that sample for future use and for those decades of investigations that the science team is so looking forward to. I'd like to introduce Mike Donnelly next. He's the OSIRIS-Rex project manager, and he'll tell you about the rest of the instrument suite and the ongoing activities at Kennedy Space Center.
Thank you, Rich. So in addition to the TAG-SAM and the SRC, there are also 5 instruments on the spacecraft that enable the science that Dante, Christina, and Jeff talked about. Let's start the video, please. On the top deck, you'll see all those instruments. So from the University of Arizona, we have 3 visible light cameras. They make up the OCAMs, which is the OSIRIS-Rex camera suite. There's the PolyCam, the MapCam, and the Sample Cam, also known as SAMCAM. From Arizona State University, we have one of the 2 spectrometers that Dante mentioned. So they're providing the OSIRIS-Rex thermal emission spectrometer, and it looks at wavelengths from 5 to 50 microns. The other spectrometer is the OVIRS instrument, the OSIRIS-Rex visible and infrared spectrometer, and it covers the wavelengths from 0.4 to 4.2 microns. So between those 2 spectrometers, we're covering a wide range from visible to the near IR. From our Canadian partners, CSA, we have the OSIRIS-Rex laser altimeter, and their contractor was McDonald Detweiler and Associates, so they've given us the OLA, the laser altimeter. And from a combined MIT and Harvard team of students, we get the regolith X-ray imaging spectrometer. And so that is the Rexus instrument, and it measures elemental abundances via X-ray fluorescence off the asteroid. So those are the instruments that also enable the science that the TAG-SAM head is going to collect the sample, and all the activity that Dante had mentioned before that made up the acronym, that's how we're doing it. And so picking up where Rich left off with the delivery of the spacecraft to KSC, if you could start the next video, please. In the evening on May 20th, we landed at the shuttle landing facility. The shipping container was taken over to the Payload Hazardous Support Facility, the PHSF, and the next morning the spacecraft was removed from that. Over that period of time from May 20th up until now, we've done a spin balance test on it to make sure that we understand what the weight and CG is. We've taken off the arrays, we've cleaned them, we've inspected them, they've been put back on. The spacecraft has been fueled, all the thermal blankets are on the spacecraft now. Next week, we start integrated operations with the ULA rocket, or with the fairing. So on the 23rd and 24th. So on the 23rd, we get integrated to the payload adapter. The 24th and the 25th, we get put into the fairing. On the 26th, we get lifted to the transporter. And then early the following Monday, on the 29th, we make our trip out to the vertical integration facility. Finally, we're going to launch this thing on September 8th, so if you could start the next video. 7:05 p.m., we'll lift off on an Atlas V 411, so that's a 4-meter fairing with one solid. About 4 minutes into the rocket leaving the Earth, the booster will burn out. It'll separate. The Centaur will fire. We'll have 2 Centaur firings. About 41 minutes into flight, the Centaur will burn out. 59 minutes into flight, we separate from the Centaur. And then it'll take on the order of 17 minutes for us to damp our rates, deploy the solar array, and move into a calm attitude so that we can actually say that the spacecraft is safe. From that point forward, we start our trip to Bennu. And so with that, I will turn it back over to Dwayne.
Thank you, Mike. And if you're just joining us, you're watching a news briefing, pre-launch news briefing from NASA headquarters in Washington. Save the date, September 8th, to an asteroid and back. Now we're going to open it up for questions, and we're going to start here. If we have any media representatives, I know we have a number of media representatives on the phone sending in your questions, and my colleagues here will be helping me facilitate those questions, and Gordon Johnston, the program executive, will be helping me to triage the questions. So, do we have any questions here? You're raising your hand. If you could wait for the mic, please give your name and affiliation, and if you can identify, if possible, who you want to answer the question.
This is Ramin Skiba with Nature. This is a question for Dante Lauretta, or if anyone else wants to comment as well, that's great. I was wondering, what does OSIRIS-Rex mean for asteroid mining? Presumably, companies like Planetary Resources and Deep Space Industries will be following closely and seeing whether a sample can be brought back and what's in it.
OSIRIS-Rex is really a trailblazer for all future small body missions. We've developed an enormous amount of proximity operations technologies, both on the spacecraft and on the ground system, to overcome the challenges of accurately navigating a vehicle like this in the microgravity environment. In fact, it's one of the key challenges that the OSIRIS-Rex mission faces. So any team that's going out there and planning to interact intimately with an asteroid, whether you're planning on mining it, your future exploration, or you're returning something back to the Earth, they're going to take great advantage of all of these pioneering techniques that OSIRIS-Rex has developed. So that's how I look at it as our, kind of one of our gifts to the future.
Thank you.
I'll grab it.
Name and affiliation, please.
Hi, Ray Bichelle with NPR. Could you briefly talk about what presidential changes, congressional changes might mean for the funding of this project?
Well, I'll take a shot at that. Of course, Congress has the power of the purse, and we respond to that. But this mission is built. It's ready to be launched. Will be launched in September. and will be on its way to the asteroid. And we don't anticipate any issues or problems, with future funding to complete the mission that we've started.
And you said it's $800 million total?
Total, yes. And that's most of that already spent.
Thank you.
Oh, okay, I'm going to come back here, but what I want to do now is we have a number of questions on social media, and then we're going to get some of the mainstream media who are on the call. So I'm going to ask my colleague Aries Keck from the Goddard Space Flight Center. Aries, what you got?
Okay, so I'm going to combine two in one question. They're both coming in from hashtag AskNASA. One comes from @VicIsMineKBy, and they ask, what makes Bennu so special? And another question we've received is, why is it named Bennu? Who got to name it?
So Christina, would you answer the why is it special, and then Dante, you can answer the how it was named.
Sure. So I'll start off with why Bennu is so special, not only because it's easily accessible for us and because it's the right size, but it's really about the composition. It's about the fact that this is a space rock that is primitive, that dates back to, over 4.5 billion years ago, and it's carbon rich. So we know there's potential for organic molecules to be there within that material we bring back. So it's important because it helps us understand really the formation of our solar system. That's kind of a big deal. Yeah. Go ahead, Dante.
And for the asteroid named Bennu, asteroids are named by the discoverer. And in this case, the asteroid was originally designated 1999 RQ-36, which is really a catalog number that indicates the time and date of discovery. It was discovered by the Linear Asteroid Survey, which is one of many successful NASA-funded surveys in the Near Earth Object Observation Program. And after we selected it as the target of our mission, we worked with Linear, we worked with the University of Arizona and the Planetary Society and NASA headquarters to run an international naming contest. And we received over 8,000 entries. Many of them were awesome asteroid names. I couldn't believe there weren't asteroids already named some of the submissions that we got. We chose Bennu because it ties into the OSIRIS. It's an Egyptian heron that's related to our theme on the mission. And the winner was Michael Puzio from North Carolina, and he said that the spacecraft looked like a heron in flight when it went to go down and capture the sample. So we thought that was a really excellent connection between our engineering, our science, and our themes, and that was why it was the winner of the contest.
Okay, we're going to come back. Gentleman here. Do you have the mic behind you? Name and affiliation, please.
Hi, Paul Vuzen from Science. Dante, I was wondering if you can elaborate why this asteroid is useful scientifically versus the meteorites that might be associated with it.
Yeah, I started my career in meteorite science, and for over a decade that was my primary focus. And so when I was asked by the original principal investigator, Michael Drake, to be his deputy early in 2004, I knew right away why we wanted an asteroid sample return mission, because we were frustrated in meteorite science by several key things. One is meteorites are uncontrolled samples. You don't know where they came from. They have to pass through the Earth's atmosphere. They experience alteration as a result of that very energetic and dynamic process. They disrupt in the air. They get scattered over large footprints on the surface of the Earth. And they're usually controlled in an uncollected way. So there's immediately contamination introduced into those samples. And our science objectives are about ultra-trace organic compounds and really understanding the role these might have played in the origin of life. I compare it to a forensic investigation. With OSIRIS-Rex, we will have control of the evidence from the time it was on the surface of the asteroid until it gets into our laboratories. So any contamination concerns are mitigated by that very careful handling.
Did I also see that the idea for the mission originated at Lockheed Martin back in the day? I was just curious about that early history.
Sure. Absolutely. Lockheed Martin approached the University of Arizona in 2004 to partner with them on an asteroid sample return mission. I was fortunate to be brought into that conversation very early, and we joined forces, brought in the Goddard Space Flight Center to capture their expertise, and over the next 7 years, the team worked diligently to write proposals to NASA until we were selected as the third New Frontiers mission.
All right, we're going to take one more question from social media, and I know we've got media who have sent in their questions, and we're going to go to my other colleague, Emily, who is going to provide those questions from the media. And the media, you are watching this program, you will hear the answers. So, Aries, social media.
Okay. We received a question from @ScriptunaPhoto, And this question is, how will you get the spacecraft close enough for the arm to reach the asteroid?
Rich, you want to take that since you're...
Sure. So as I said, we go through actually a series of maneuvers. The great thing about Bennu is it's big enough that we can actually go into an orbit around it. And once we leave the orbit around it, we actually do a series of maneuvers. There's 2 additional maneuvers that we do that both match the asteroid's spin rate and then put us on a trajectory where we go down towards the asteroid. So we actually do take thrusters and push ourselves gently towards the asteroid. When we're moving towards the asteroid, we're actually only moving 10 centimeters a second. Now, how fast is that? So it turns out that's about 1/4 of a mile of an hour. So the 1 lap around the track analogy, if you took an hour to walk around a track, that's how fast we're moving in order to go down and collect that sample.
Okay, Emily, we've got lots of media questions. Let's go down the list.
Cool. This first one is from Emily Lakdawala from the Planetary Society, and there are a couple different parts to it. So what significant events are we looking forward to after spacecraft separation? How soon do solar panels open? And when does instrument commissioning start? And are we going to try to take any photos of Earth as we depart?
She got a lot of questions.
I can repeat any of those.
So I don't recall the exact timing of everything, and I don't have it in a series of notes here, but 59 minutes after launch, we separate from the rocket. And immediately, we will start rate damping. Once we've damped the rates, and so that's going to take on the order of 1 or 2 minutes, we will start the deployment sequence for the 2 solar. That's a very quick operation. So that's another 1 to 2 minutes, and they're out. Then the longest activity is actually to get the spacecraft into a calm, friendly attitude once we've been released so that we can connect up to the DSN, we can get the telemetry down, we can send commands in, we can verify that the spacecraft is safe. So like I said, about 1 hour and 17 minutes after launch, we will know that the spacecraft is healthy and is ready to go. We will check out the instruments around 14 days after launch, and that's just turning them on, making sure they're still functional, and then we'll turn them back off. When we come around for the Earth gravity assist, that's an opportunity for us to do some calibration activities with the instruments, but that is a year later after launch. So we'll probably start that planning around 6 months or so after launch, I believe.
Next.
I will just mention, I'll just add to that, that we do plan to acquire images of the Earth as we come by for that Earth flyby. So we will, that is part of the plan as it stands now.
And the rocket has cameras on it, so you'll see the same views that you've seen on all the Atlas launches where it's going up. They have cameras on the booster looking down.
Great. This next question is from Jason Major of Discovery News and Universe Today, and he asks, what will happen to the OSIRIS-Rex spacecraft after sample return, and is there a chance for extended missions?
Wow.
Why don't you take that, Dante?
Okay, so as we're coming in for the Earth return, we have a very precise corridor so that we line up the sample return capsule for the right angle of attack to make sure it lands safely in the Utah test and training range. So that really drives the trajectory of the spacecraft. That said, right after we separate, we'll do a deflection maneuver and the spacecraft will be put into a parking orbit around the sun. Currently, the team has no plans for an extended mission. However, we expect that it'll be a healthy spacecraft and fully functional, and it'll really be up to the agency to decide what kind of extended missions they might be interested in for that vehicle.
Great. This next one is from Sarah Hammond of Arizona Public Media, and she asks, what will be the first image captured by OSIRIS-Rex, and what is its importance?
You want to take that one, Dundee?
Yeah, the first images from the OCAM's suite will be calibration images, so we'll be looking at star clusters. We're trying to understand the alignments of the instruments that may have shifted slightly during the launch and do some final calibrations for geometric distortions and other critical imaging parameters. So there'll be great images of star fields about 6 months after we launch.
And then I'll just add to that, a year after launch, we will have the images of the Earth flyby. And as I mentioned, in August of 2018 is when the highest res, the Polycam will be able to get a single pixel on Bennu and begin the actual observations of Bennu. And I think one of the significant parts of those first observations is pinning down exactly where Bennu is for navigation purposes.
Let's take a few more media questions, and then we'll take one more social, and then we'll wrap it up. Go ahead, Emma.
Great. This next one is from Jim Nitzel from Tuscan Weekly, and he asks, can the panelists talk a little bit about working with the University of Arizona on the OSIRIS-Rex mission?
It's been wonderful. Dante has done some excellent leadership on the mission and also working with our other instrument partners, the two universities that we're dealing with, our Canadian partners, the Goddard team, and especially with Lockheed. Everybody, it's been a very good relationship, very cordial, very professional, and we've successfully completed this mission on time, and we've delivered it under budget. So I would say it's been very successful.
Yeah, and I'll just add to that. You know, I mentioned earlier on that I was originally a deputy principal investigator, and I worked with my mentor, Mike Drake, for 7 years. He passed away in September of 2011, and that's when I accepted the role as principal investigator. And he and I really believed in the one-team philosophy, and we have achieved that. You know, we are not Arizona, Lockheed Martin, NASA, Goddard. We are OSIRIS-Rex, and that is why this mission has been so incredibly successful in our development, and why I expect that will continue as we go into operations.
Emily?
Great. This one's from Bart Leahy from Spaceflight Insider, and he said, what propulsion systems will OSIRIS-Rex use to maneuver around the asteroid and send the sample back to Earth?
I think that's... Go ahead.
Sorry. So we're a blow-down hydrazine system. So we use a monopropellant system. We have 28 thrusters ranging from 0.2 newtons to 200 newtons of thrust that we're going to use to navigate around Bennu and make sure we get there, as well as make sure that we return safely.
Great. This last one is from Greg Redfern of WTOP, and he asks, what is the most exciting finding you expect from the mission? And he also asks, are there any aspects of Bennu that separate it from other carbon asteroids like Murchison? I'm not sure if I said that correctly.
You want to answer that, Dante?
Well, the most exciting thing about any planetary exploration mission is that you're going to a new world with Bennu. I mean, we know a lot about it from our astronomical campaign, but we're also expecting that we're going to require some time to map it and understand it and study it so that we can get the best sample possible. For me, the mission is driven by the return of pristine organic molecules from the early solar system. So I'm really hopeful that we will get some unique material that isn't in our meteorite collections, because it's probably friable, not easily surviving atmospheric passage, and that's one of the reasons we're going to protect it in our sample return capsule. So it really is a great adventure. We're going out into the unknown. We are bringing back scientific treasure. And for me, looking forward to the day in 2023 when we open up that sample return capsule is what's driven me for the past 12 years and what's going to keep this going for the next 7.
And can I add, we gathered the Apollo samples starting almost 50 years ago, and we're still making discoveries by analyzing those samples all the time. And that will be the legacy here too. We'll meet the mission goals of better understanding the origin of the solar system and the other things we've spoken about, but the discoveries are going to keep coming for lifetimes, because we have one of the best curation facilities in the world at Johnson Space Center, and the samples will be made available to scientists everywhere around the world. And that, ultimately, there's going to be a legacy that one can't even predict.
A couple more questions from social media areas, and we'll close out.
Okay, the first one is from @CombatWeather. Is there any potential to receive more than 60 grams of material in the return sample?
Well, I can address that, and anyone can correct me, but in some of our tests, we've gotten up to 2 kilograms of material. So it could be up to 4.4 pounds, depending on the density of the material and how easily it's motivated by the gas as we do the sampling.
Yeah, and I'll add to that. I've watched the TAG-SAM development from those early days where it was a solo cup and an air compressor to the phenomenal flight unit that we have today. And 60 grams is, I've never seen a test that low in the TAG-SAM sample collection. They actually designed it to pick up 150 grams to give us a lot of margin on the engineering side of that, and routinely picking up several hundred grams, so 5-6 times the 2 ounces of material that the scientists required to get our mission objective completed.
Can I throw in one more?
No, let me take this social media question here. Good.
Okay, and now this question is from @Spork62, and they ask, could we expect any missions in the future based on the findings of OSIRIS-Rex?
I'll address that. I mean, I'd have to say yes. I mean, NASA turns to the National Academy of Sciences to set our science priorities, to making sure we're working on the most important questions for the nation. And, but I fully expect that the fabulous discoveries of the OSIRIS-Rex mission will open up new questions that will then be reflected in future decadal surveys and future missions.
Final question. Wait for the mic.
Thank you. Could you, I don't remember who was talking about the Yarkovsky effect, but could you go into a little bit more detail about what it is you hope to understand about the effect from this mission and how you know that that would apply to other asteroids for which you don't have such good information on composition and properties?
Sure, I'll take that. So the OSIRIS-Rex team has done a phenomenal job characterizing the Yarkovsky effect on asteroid Bennu. And that's really because we have a nice long arc of observations. The first observations were taken in 1999, including the Arecibo planetary radar system, which gave us direct range. We repeated those in 2005 and 2011. And that allowed us to measure directly the Yarkovsky drift on Bennu over that 12-year time frame. What we're going to do is we're going to extend that arc all the way out to 2018 through 2021. So we'll have over 20 years of very precise tracking data on this asteroid. So it's what we call the signal-to-noise ratio. The detection of the Yarkovsky effect will go up to over 400, a phenomenal, unprecedented scientific result. But more than that, we have a theory of how the Yarkovsky effect works right now, which is absorption of solar radiation, re-emission of thermal radiation. But remember, we've got the OVIRS, visible and infrared spectrometer, we've got the OTEST, thermal emission spectrometer, and we've got OLA and OCAMs. When you combine all of that data together, we're going to have a great model of the thermophysical properties of the asteroid. Its rotation state, its orbit will be really well defined, and we're going to see if theory matches observations. And if it does, then we have great confidence that we understand the details of how the Yarkovsky effect works. If it doesn't, and sometimes nature surprises you, we're going to have to go back and sharpen our pencils and refine our theory until we get to the right answer, till we can match observations with our theory. So once we have that theory well grounded, then it will be much more applicable to asteroids across the solar system.
And the main use of understanding that in detail is to, I'll repeat, the main use of understanding the Yarkovsky effect in how it works in reality is to be able to predict the path of asteroids?
Yeah, the Yarkovsky effect turns out to be a fundamental process that's affecting these small asteroids across our solar system. And so the applications have been varied. One of the most fascinating ones for me is that asteroid families in the main asteroid belt formed as collisions of two objects, catastrophic disruption with many thousands of small asteroids created. Well, the Yarkovsky effect is stronger on smaller asteroids. And so we see these asteroid families spreading out as a result of the Yarkovsky effect, and that actually works as a chronometer, so we can now date when these collisions took place in the main asteroid belt by tracking the Yarkovsky effect, pushing the smaller pieces farther away from the point of that collision. That's an awesome result. We're dating events that happened 800 million, a billion years ago, and in fact, we have tracked down the origin of Bennu to one of two such collisions in the asteroid belt in two different asteroid families. So that's fundamental to NASA's objective of understanding the workings of our solar system and how these small bodies migrate, and ultimately getting into a resonance with the gravity field of Jupiter or Saturn and then flung in to become near-Earth objects. Once that happens, you want to know where they're going to be very precisely in the future because it's part of impact hazard assessment. And if you don't have that in the equation when you're predicting asteroid trajectories out to the future, you're not going to know exactly where that asteroid is going to be. So it kind of has multiple applications across solar system science.
Thanks.
Well, thank you. I want to thank our panelists. I want to thank our worldwide audience for joining us. You've been listening to an Asteroid and Back. All of the information that was presented here is available online at www.nasa.gov/OSIRIS-REX. All systems are go for a launch on September 8th down in Florida. To an Asteroid and Back. Ladies and gentlemen, another NASA science mission to the solar system and beyond. We're out there. Thanks for joining us.